Imagine for a second that the past, well, that it isn't just memories fading away, but maybe something, more solid, woven into reality itself. You are always curious learner. Ask this really, really fascinating question. Could quantum computers one day, like, decode past quantum states?
Right.
Makes you think, doesn't it? Like there's some hidden history book just waiting for us.
It's a brilliant question, and it really pushes us right to the edge, doesn't it? To the limits of what we understand about physics right now.
Not yet.
So today, yeah, let's do a deep dive into this. It's pretty ambitious. We'll explore maybe two connected areas. First, this kind of mind-bending idea of the universe as like a giant computer, and second, the amazing progress in quantum computing, trying to actually manipulate those fundamental bits of reality quantum states.
Exactly. And we've got some really great stuff to dig into here. We're looking at quantum dots theory, gives us a close look at manipulating matter down at the quantum level. The kind of control you'd need. Then there's total recall via the quantum realm, which tackles your question head on about accessing past quantum info. And universe as Planck scale computation 1, that lays out this incredible idea that reality itself might just be information processing. So our mission, like you said so well, is figuring out the feasibility, maybe, of seeing through the looking glass of quantum entanglement networks to reconstruct past events. Okay, let's start unpacking this idea of the universe as a computer.
Wow.
Wow.
Yeah, what's really gripping here is the thought that maybe at the most basic level, the universe isn't really about matter and energy as we usually think of them, but maybe it's information. This whole idea of digital physics, it basically says the universe works like a huge computation,
Yeah.
processing discrete little chunks of information, like bits in your laptop, but on a cosmic scale.
So not a stage with actors, but a colossal program just running.
Kind of, yeah. And if you think about it that way, it totally changes how you view the past. It's not just gone. It's maybe just a previous state of the information.
It's a pretty wild concept, but, it's not totally out of the blue, is it? Our source on the computational universe mentions thinkers way back, Conrad Zuse in the 60s, Edward Fredkin.
Fredkin, yeah, in the 70s, they were really pushing this digital physics view.
And it even connects back philosophically, right, to Plato, Descartes, this whole idea of an underlying order to reality.
Exactly. Humans have always wanted to find that fundamental order, those basic rules. Digital physics is sort of framing that search using information theory. And where this gets really, really significant is when we start talking about the Planck scale.
Okay, the Planck scale. Right. For anyone maybe not pondering the infinitesimally small over breakfast, what exactly is that?
Yeah, think of it as like the ultimate frontier of physics as we know it. It's this realm where quantum mechanics and gravity are supposed to be equally important players. And it's where our current theories, well, they kind of give up. We're talking the Planck lengths, that's about 1.6 times 10 to the minus 35 meters. Unimaginably small.
Minus 35. Wow.
Yeah, and Planck time is just as tiny, about 5.4 times 10 to the minus 44 seconds. These aren't just random numbers. They come from the fundamental constants of nature, like the speed of light, Planck's constant.
So down at these scales, our smooth picture of space and time might actually be grainy, pixelated.
That's the idea, yeah. Some theories trying to unite gravity and quantum mechanics, like loop quantum gravity,
Yeah.
OQG, they suggest exactly that. Instead of smooth space-time, maybe it's made of fundamental units, grains of space, woven into these things called spin networks.
Spin networks.
And in that picture, properties we think of as continuous, like area, might actually be quantized, meaning they can only have specific, discrete values, like steps on a staircase, not a smooth ramp.
Okay, this is where it gets really interesting for me. Because if space-time itself is built from these discrete bits, doesn't that make the computational universe idea seem, well, more plausible?
It definitely paints a more compelling picture, doesn't it? If reality is fundamentally discrete, chunked up, then the idea of it running on computational rules processing these chunks feels more natural. But, and this is a big but, we have to remember this whole discrete versus continuous spacetime thing is still a massive debate.
Right, because our everyday experience and most of physics works perfectly fine assuming space and time are smooth. And our source mentions experiments, right? Looking at light from distant galaxies. They haven't found any obvious signs of this pixelation yet, at least at scales we can probe.
Exactly. And there are theoretical hurdles too. Like how do you make a discrete spacetime work with Einstein's relativity? Specifically something called Lorentz symmetry. The idea that physics looks the same no matter how you're moving uniformly. A pixelated spacetime might mess with that symmetry in tiny ways, and, well, we just haven't seen evidence for that yet.
Okay, so Intriguing connections between quantum gravity and a computational universe, but still very much an open question. But the sources also bring up another really fascinating angle. What if gravity itself isn't fundamental? What if it emerges from all this computation?
Yes. This is a super exciting area. Melvin Vopson's theory, for example. He suggests gravity might pop out of a basic principle about information, specifically minimizing information entropy. The universe, in this view, is constantly trying to be more informationally efficient, tidier.
So it's like information wants to clump together to be described more simply, and that pull is what we feel is gravity, like a cosmic decluttering force.
Huh. It's a brilliant way to put it, a cosmic declutterer. Vopson talks about his second law of infodynamics, and interestingly, he proposes that information entropy in an isolated system tends to decrease or stay level, kind of the opposite of thermodynamic entropy. And using that, he argues you can actually derive Newton's law of gravity. It arises from this drive to minimize the system's information content.
Wow. That completely flips the script. Gravity not as a fundamental force needing a graviton particle, but as a side effect of information organizing itself. And if gravity could emerge like that, what about the other forces? Electromagnetism, the nuclear forces.
Well, that's the grand hope, isn't it? The computational framework might offer a path to unifying all four forces. Our standard model describes the other three beautifully, but gravity's always been the odd one out. If everything boils down to information processing at the Planck scale, maybe all these forces are just different ways that information interacts or structures itself.
Different rules in the cosmic code, maybe? Giving rise to different forces. It's a huge vision. But, okay, let's pull this back to your original question, learner. Decoding the past with quantum computers. How does this computational universe idea link to the practical challenge of manipulating quantum states?
Well, if the universe is processing information, and quantum states are the basic units of that information, then yeah, understanding and controlling those states is fundamental. It's the key to potentially reading the universe's log files, so to speak.
So now let's pivot and look at quantum computing itself and what it might actually let us do in terms of time reversal.
Okay, right. So moving from the deep theory of reality to the tech being built to harness quantum weirdness, if we want to reverse time in a quantum system, what's the basic physics principle involved?
The core idea comes from something called unitarity. In a perfect quantum system, one totally isolated from everything else. Its evolution is described by unitary math. And unitary evolution is fundamentally reversible. If you knew the exact quantum state perfectly at one time, you could mathematically run the clock backward and find its past state. In theory.
But perfectly isolated.
Ugh.
That sounds like the catch. Like
Right.
trying to unscramble an egg perfectly. The real world messes things up, right? Decoherence. Exactly. That's the killer in practice. Real quantum systems always leak information into their environment, interact with stuff. That causes decoherence, this loss of the pure quantumness you need for perfect reversal. So right now, our main tool for figuring out an unknown quantum state is something called quantum state tomography.
Quantum state tomography. Sounds complex. What's the gist?
The gist is you need many, many identical copies of the quantum system you want to understand. Then you perform lots of different types of measurements across all those copies. By looking at the statistics of all those measurement results, you can piece together a picture of the original quantum state, often mathematically represented by something called a density matrix.
Okay, so it's like building a 3D model from lots of 2D photos taken from different angles. But it doesn't really let you watch the undisturbed history of just one system unfolding, does it? Because you're constantly measuring and disturbing copies.
That's a key limitation, yeah. It gives you snapshots, but not necessarily the pristine movie of a single event's past without interfering. But there's another angle here, the holographic idea. It suggests that maybe, just maybe, the entire history of a system is encoded in the pattern of entanglement across all its parts. Like every interaction leaves a tiny mark, an imprint on how the qubits are connected.
A quantum fingerprint of the past. I like that. And if we could somehow read those fingerprints.
Then hypothetically, yes, you might be able to piece together what happened before. But trying to actually do that with a quantum computer, that's a whole other level of challenge. It needs some serious technological leaps.
Okay, let's talk hardware. What kind of quantum computer, what kind of setup would we even need to start thinking about decoding past states from entanglement?
Right. First off, fault-tolerant quantum computers. Not just a handful of qubits. We're talking probably thousands, maybe more, of really high-quality qubits. And they need to be incredibly well protected from noise, using quantum error correction, QEC. Our source mentioned AI, like Google DeepMind's work, potentially playing a big role in making QEC work effectively. That's absolutely crucial.
Thousands of qubits.
So,
Yeah, we're currently talking dozens, maybe low hundreds in the best labs. That's a
yeah,
big leap. What else is on the shopping list for this quantum time machine?
long-lived quantum memory. That's another huge one. You need to store these delicate, entangled states for a long time without them. Well, decohering, losing their quantumness. Technologies like superconducting qubits, kept near absolute zero, or trapped ions held by lasers. They're promising candidates, but need improvement for really long storage times.
Makes sense. Can't decode the past if the clues fade away before you can even look at them. What about actually reading the clues, those entanglement patterns?
You need ultra-precise ways to measure, ideally something called quantum non-demolition measurements, or QND. It's about measuring some property of the system without completely destroying its overall quantum state in the process. Techniques like weak measurement are exploring this. It's super delicate work.
Gently peeking without breaking it. Sounds tough. And how would you actually put all this together to reconstruct the past state?
It would probably have to be some kind of continuous process, integrating that quantum state tomography we mentioned with very advanced quantum simulations. You'd need to constantly monitor and record the state, building up these massive data sets. Then you'd need powerful quantum algorithms to crunch that data and essentially run the simulation backward, which also means you need incredibly fast detectors and the ability to handle just enormous amounts of quantum data.
And I guess managing all that, figuring out the rewind algorithm, that needs serious computing power itself, right? Both quantum and maybe classical AI working together.
Oh, absolutely. You'd need extremely sophisticated computational design. AI would almost certainly be essential, helping to spot patterns in those super complex entanglement networks, optimizing the algorithms needed to invert the evolution, maybe even helping to correct for the inevitable leftover errors and decoherence.
It really sounds like a whole ecosystem of bleeding edge quantum tech needing to work in perfect harmony. But our source material also flags some really fundamental challenges, right? Things we can't just engineer away easily.
That's right. Isolation and decoherence are always going to be the enemy. You can shield things, you can use error correction, but eliminating environmental interaction completely in the real world, probably impossible. Then there's just the sheer scale of the data. Tracking the entanglement state of thousands of qubits over time,
Mhm.
where do you even store that? We might need something people are calling a quantum hard drive, which is still very much sci-fi territory.
A quantum hard drive.
What?
Wow. And even if you had the perfect data storage and retrieval, running the evolution backward, the algorithm itself sounds incredibly hard.
It is. Algorithmic inversion, efficiently reversing quantum evolution, is a major theoretical challenge. But there are promising frameworks being developed, things like quantum singular value transformation, or QSVT. QSVT is basically a toolbox of quantum techniques that might allow future quantum computers to efficiently undo certain types of quantum operations, which is exactly what you'd need for time reversal.
So it's like having a quantum undo button framework.
Kind of, yeah. For
Mhm.
specific types of operations. It's a key piece of the puzzle if you want to computationally go backward in time.
It's just fascinating that even though the big goal sounds like pure fiction, there's real, solid research chipping away at the foundational pieces. The source mentioned things like QURA, too. Quantum state reconstruction using unsupervised regression analysis. Sounds like AI learning to predict reversed quantum dynamics.
Exactly. QRA, QSVT, better quantum memories using different qubit types, AI helping with error correction. All these threads are being pursued. They're laying the groundwork piece by piece, even if the final picture, like that quantum hard drive for entanglement history, is still way off.
So, okay, wrapping this deep dive up. We've gone on quite the journey, haven't we? From this huge idea of the universe as a giant computer running at the Planck scale, where gravity might just be information doing its thing,
Okay.
all the way to the nitty-gritty, the really tough challenges of building quantum computers that could maybe, just maybe, manipulate and reverse quantum history.
And I think we've seen that while the computational universe idea is, well, mind-blowing background music,
Mm.
the actual job of decoding the past with entanglement. It faces just enormous hurdles, both theoretical and technological. Literal total recall of past quantum states. That's definitely still in the realm of highly ambitious, very long-term goals.
But for you, learner, the big takeaway here is maybe just how interconnected everything is in fundamental physics. From the tiniest scales of quantum gravity up to the cutting edge of building quantum machines, it's all part of the same quest to figure out reality. And who knows what incredible aha moments are still waiting down the road as we keep pushing.
Indeed. And it leaves you with a final thought, doesn't it? If the universe is some kind of computation, what are its ultimate limits? How much can it compute? How much can it remember? And could accessing past quantum states, if we ever manage it, be like finding the universe's command line? Or accessing its system memory? It certainly makes you want to keep learning about quantum information, quantum gravity, and where quantum computing is headed next.